In this screencast, I'd like to look at solving systems of equations with matrices. Here is our system, x plus 3y is 11 and 2x minus y is 1. First, I'd like to get a geometric interpretation of what this system means. What we have is we've got a line and a line. We're going to draw those two lines. If I let y be 0, x would have to be 11. And if I let x be 0, y would have to be 11 thirds. So that gives us a line with a negative slope. In the next one, we've got if y is 0, x would have to be a half. And if x is 0, y would have to be negative 1, which means we get another line, this time positive slope. Those two lines intersect at a point. That point is the point we're after when we try and find our solution. So first, before we solve it, we're going to look at rewriting this in a couple of ways. One way is if I think of x as the constant times by a vector, I'm going to write this as x times by the vector 1, 2. And also take y and multiply it by the vector 3, negative 1. And that should equal the vector 11, 1. Notice that I have a linear combination on the left, and I'm asking when is the linear combination on the left equal to the vector on the right? How can I write 11, 1 as a linear combination of 1, 2, and 3, negative 1? Because it's a linear combination, we could rewrite it in matrix form. If I just take the 1, 2 and the 3, negative 1, multiply those by the constants, x, y, and then set that equal to 11, 1. This is now a matrix equation I can use to solve the system. Really, it's now xy times by this matrix on the left needs to be 11, 1. This matrix on the left is called the coefficient matrix, and we'll be using that throughout the semester. We can also rewrite this without writing the equal sign and the extra vector in the middle if we just want to focus on the constants. By just writing everything, write the columns in and write the 11, 1 in, and often people put a line in the middle to say, hey, I just replaced the equal sign in all of this with just that line. This is called the augmented matrix of the system, and it's that augmented matrix we're going to be using as we try and solve that system. So first let's solve the system. We're going to use an elimination method to do it. And then once we've finished, we're going to repeat that by looking at the matrix approach, and that matrix approach is the one we'll be generalizing throughout the semester. The idea of elimination is let's use one of the rows, let's use the variable x here, to eliminate the x's from the other equations. And so the idea, if I take 2, if I take row 2, and I subtract 2 row 1s from it, so take this and minus 2 of those, that'll end up with a 0x. Well, if I take this and minus 2 of those, it gets me a minus 7y, and if I take that and minus 2 of those, it gets me a 1 minus 22 and negative 21. That right there tells me, well, one, it gives me a way to eliminate x from the second equation. I can now take this equation, and if I take that equation, I need a name for it. I'm going to call this row 1. I'm going to call this row 2. Now I took row 2 and I modified it, so I'm going to call this row 2 prime. If I take row 2 prime and I divide it by negative 7, I've modified it again, so I'll call it row 2 double prime. That gives me y equals 3. I now have one of the equations that I need. Now I'm going to rewrite my system. I've got x plus 3y is 11. That's my row 1. And I've got my row 2 double prime, which is just y equals 3. I take this system now, and I'm going to try and modify row 1. I'm going to use the y here to eliminate the y from the other equation. So we'll take our row 1, and I'm going to subtract 3 times row 2 double primes. If I do that, I'm trying to eliminate this. I've got x minus nothing, 3y minus 3y is 0y, and then, oh, I had an 11, I better remember it. 11 minus 3 times 3, 9, that's 2. I'm going to rewrite that. This is now a row 1 prime, and this is row 2 double prime. I have my system's solution. X is 2, y is 3. That tells me precisely what the point is. It also tells me how do I create 11, 1 as a linear combination of 1, 2, and 3, negative 1. It also tells me how I solve this matrix system. I put the number 2 here and the number 3 there. Those two numbers tell me precisely how to solve 3 different problems. We're not going to repeat this in matrix form. If I just take my augmented matrix, 1, 3, 11, 2, negative 1, 1. And I do the exact same thing before. I want to eliminate the 2 by using the 1, so I'll take row 2 and I'm going to subtract 2 row 1s. I'm changing row 2, so I'm going to replace row 2 as I go along. And I'll replace row 2 with the new row. So that one minus that is 0. This one minus 2 of those is negative 7. That minus 2 of those is negative 21. Now I'm going to take row 2 and I'm going to divide by negative 7. 1, 3, 11, leave the row 1 alone. And row 2 I'm changing 0, 1, 3. Well, that's precisely what we got before. Now we're going to use the 1 here to eliminate the 3. So I'm going to take row 1 minus 3, row 2. 1, 0. 11 minus 9 is 2, 0, 1, 3. And again, I now have the I have y equals 3, and I have x equals 2. This equation you could rewrite as 1x plus 0y is 2. You can write 0x plus 1y is 3, which is the same thing as x is 2, y is 3. We now have our solution using just matrices. You can either use systems or you can use matrices. The advantage of using matrices is you don't have to keep track of the variables, the equal signs. You can write much less. This becomes an algorithm you can code into a computer fairly quickly. This method is what will become called Gaussian elimination. We'll be looking at that in the next screencast.